Hi, folks. Today we're going to talk about number theory. Now, number theory is a very interesting and complicated subject, as are most of the ones we focus on in this course. Uh, Number theory broadly deals with the properties of different sets of numbers. Typically, we focus on things like the integers, rational numbers, and algebraic numbers. But we also focus on the idea of countable sets. Uh, and so we'll discuss what the difference between countable and uncountable is. But in that we focus on countable sets, it makes this one of the major branches of discrete math, which focuses on countable objects. When we think about what we're going to be talking about here, most of it's going to focus on the idea of prime numbers, because that's really what's at the heart of number theory. It's all about the structure of numbers. And prime numbers are the main structure of numbers. And so oftentimes the majority of this material I would introduce in a pre-algebra course, but we can handle a little bit higher. And so we're going to have some proof-based version of that. That said, let's talk about what is number theory. Much of the focus of introductory number theory is on the idea of primes and composites, factorization, division algorithms, greatest common divisors, least common multiples. And more advanced number theory topics can include things like quadratic residue, cryptology, the Gaussian integers, or modular arithmetic. We'll deal with a couple of those later this semester. Before we jump into it, we're going to do a couple of important properties. The first one being the well-ordering property. And so the well-ordering property says every non-empty set of positive integers has at least element. And so when we look at this, 2, 4, 6, 8, 10, is there a number which is the least element? Sure, 2. It's right there. Why do we care? Well, this property allows us to list things. The idea being if we have a set of numbers, and let's say that we've got 2,000 different numbers that we have to look at. The fact that there is a well-ordering property means that there is a smallest number that we can start looking at. This property doesn't work for positive real numbers, and so be aware of that. If you have 1/2, 1/3, 1/4, 1/5, and so on, there is no smallest element in this. You'll go on to 1/100th, 1/1,000,000th, 1/1,000,000,000,000th. You could just go as large of a value as you want, and it's going to make it so that the fraction is very, very small. In this case, there would not be a smallest value. Well, our ordering property, though, is just for integers. And so positive integers, meaning whole numbers. Yeah, note that the property doesn't work for integers in general. There is no smallest integer. You can go off to negative infinity, and you will still be able to find things much smaller. Another big one is the pigeonhole principle. The pigeonhole principle is one which we use quite a bit, but we don't often talk about it. And so if k plus 1 or more objects are placed into k boxes, then at least one box contains 2 or more of the objects. The reason it's called the pigeonhole principle, let's say that you have 25 holes for pigeons and you have 26 pigeons. One of the holes is going to have 2 pigeons. We use this trick to prove a lot of things. So here's a simple example. Consider a listing of 3 positive integers. Then either 2 of them are odd or 2 of them are even. Now you might sit there and think about it for a second and then be like, yeah, that checks out. Well, if we want, we can prove this using the pigeonhole principle. And so we have 2 boxes in this case, odd and even, and 3 objects, positive integers. Each object has to go into one of the boxes. As such, 2 of them are either odd or 2 of them are even. That's our pigeonhole principle. Let's dive into the big bits. Infinity. What is infinity? Well, infinity is a limit, and that is a calculus term which we might not be ready for quite yet, but we can at least introduce the idea so that we can talk about countability. And so in calculus, you learn that limits approach things which you approach. And so in the case of infinity, it's not a number, more the idea that there is always a bigger number. And so If you say that 100 is the last number, well, no, there's a larger number. If you say a million, well, you can always do a million plus one. And so with infinity, it's the idea that there's always going to be a larger value than whatever number you pick. We say that a set, sequence, or listing of numbers is infinite if there are an endless quantity of numbers in them. All of our popular sets of numbers have an infinite quantity of them. And so if you're talking about the natural numbers, the real numbers, any of them have an infinite number of numbers. Here are some examples. Set of whole numbers less than 10 is not infinite because it has 10 numbers in it, in particular 0 through 9. We say this is finite. The set of natural numbers is infinite because it goes on forever. The digits of pi could be considered infinite because the listing of digits goes on forever. The sequence 1/2, 1/3, and on has an infinite number of values because it also goes on forever. Now we have the idea of countable versus uncountable, and this will tweak things a little bit. And so a set is countable if either it has finite or it's infinite and there exists a one-to-one correspondence between the natural numbers and the set. And so either there's some countable, or well, can't define countable in terms of countable. Either there is a fixed number of elements, like let's say that there's 20 elements in the set. Or when we're counting how many, we can figure out what the next value is going to be. And so by correspondence, we mean we can order the numbers in some way and say that there is a first, second, etc. number on the list. Our ordered lists include all of the numbers on the set or in the set. A set that is not countable is called uncountable. And so here are some examples. The set of whole numbers less than 10 is countable because it's finite. There's only 10 of them. The sequence 1/2, 1/3, 1/4, 1/5, and so on is also countable. We could think of 1/2 as the first number, 1/3 is the second number, 1/4 is the third number, 1/5 is the fourth number. Wait, yeah, I'm getting mixed up with my numbers. But yeah, and so there is a clear order to these numbers, and so it's a countable set. The natural numbers are also countable, and so the natural numbers, they start with 1, 2, 3, 4, 5, and so on. There is a natural order to the natural numbers. That's where the name comes from. The real numbers are uncountable, and this one's a little trickier to prove, so we won't prove it here. But the idea is that there is no correspondence where we can say, oh, 1 is going to be the first value, pi is going to be the second value, square root of 3 is going to be the third value, and so on, and get every single number included in our list. There are too many numbers. We cannot determine a way to describe all of the different numbers in the set. And that's a problem. And so let's look at some of the other sets. The next set is the integers. So remember, the integers is the positive and negative whole numbers. We can create an order for this. And so the integers are a countable set. If you think about it, start at 0, then 1, -1, 2, -2, 3, -3. This listing that we're creating is going to cover all of the integers. Every single number will be hit eventually. The rational numbers are much trickier. And so if we look at what this image is that I'm showing you, I'm basically showing you an image of a chart with the numerators and denominators. The numerators are listed here on the left, and the denominators are listed on the top. And so if we wanted to figure out where, how about -2/3 is, well, we would say -2/3, and it's going to be over here in quadrant 1. Well, using this, if we start at 0/1, and then we spiral our way out. So 0/1, 0/2, -1/2, -1/1, -1/-1, 0/-1, and so on, all of the way around. And if we see any repeated values, we could just skip over them. So maybe skip over the 0/-1 since we already got 0. Well, doing this, we can create a list which will include every single rational number. And that means that this set is rational. And so, or sorry, this set is countable. There is a countable number of elements for the rationals. The reals are uncountable. We cannot create a listing which covers every single real value. And since the rationals are countable and the reals are uncountable, that tells us that the irrational numbers are also uncountable. We can't create some ordering like this that will describe all of the irrational numbers. With infinity introduced, let's talk about divisibility. And so, definition, if a and b are integers with a not equal to 0, we say that a divides b if there's an integer c such that b is equal to a times c. This might be confusing just to kind of hear it said that way because it sure looks like multiplication. And in this case, it's saying division is defined in terms of multiplication. And so a is a divisor of b if a times something is equal to b. That means that b divided by a is equal to some integer value c. And so if a divides b, we also say that a is a divisor or factor of b, and that b is a multiple of a. And so that's what connects divisibility and multiplication. As an example, we can say that 3 divides 21 because there's an integer c such that 21 is equal to 3 times c. In this case, c is 7. We can say that 3 is a factor of 21 and that 21 is a multiple of 3. Here's a fun little lemma. And so a lemma is just a fancy way of saying a small theorem. And so looking at this lemma, it says if a divides b and b divides c, then a divides c. And so since 3 divides 15 and 15 divides 20, we can say that 3 divides 60. That sounds reasonable. Can we prove it? Because remember, in mathematics, everything's about the proof. And there's a nice quick proof for it. And so since a divides b, we can say that there's some value n such that b is equal to a times n. Since b divides c, we can say that there is some value m such that c is equal to bm. Substituting, we get c is equal to a times n times m. And if we let k be equal to nm, whatever that product is, well, n times m is going to be some nice integer. And so that tells us that we get c is equal to a times k, meaning a divides c. So easy to prove. Using that, we can develop a division algorithm. And this is the division algorithm you learned in 4th grade and have been using ever since. It's just written a little differently. And so the division algorithm, if a and b are integers such that b is greater than 0, then there are unique integers q and r such that a is equal to b times q plus r, with 0 less than or equal to r less than b. We call q the quotient and r the remainder. And so whenever we divide two values and get a remainder, this is what we're really saying. We're saying that if some number divided by something else is equal to q with a remainder of r, then that number times q plus r gives us our starting value. Example, given the numbers 17 and 5, we could say that 17 is 5 times 3 plus 2. And this is the unique way to write out the expression from the division algorithm. The quotient of 17 and 5 is 3 with a remainder of 2. Given the numbers 24 and 6, we can say that 24 is equal to 6 times 4 plus 0. This would be the unique way to write out this expression. So the quotient of 24 and 6 is 4 with a remainder of 0. Another important definition, defining even and odd. And so if the remainder when n is divided by 2 is 0, then n is equal to 2k for some integer k, and we say that n is even. And so when we're dealing with integers, if the number is divisible by 2, it's even. If the remainder when n is divided by 2 is 1, then n is equal to 2k plus 1 for some integer k, and we say that n is odd. Again, we know what even and odd means. We can recognize them out in the wild. But now we have tools which we can use to prove things. For instance, can you use the definitions to prove that the product of two odd numbers is odd? It shouldn't be too bad, because if you take two odd numbers, let's say 2k plus 1 and 2l plus 1, multiply them together, boil it out, then you should be left with something which is 2 times something plus 1. And as long as you can find that that something is an integer, you have verified that it's going to be an odd value. Prime numbers. This is the main topic when you're talking about number theory. Everything boils down to prime numbers. So in mathematics, the prime numbers form the underlying structure of the natural numbers. We often think of it as being similar to the periodic table and how the periodic table describes all molecules in chemistry. And so a prime number is a natural number which has exactly two divisors. That's how it's defined. And so it has two divisors, 1 and whatever the original number is. By default, yeah, the two divisors are 1 and the number itself. But of note, 1 is not prime because it only has one divisor. A natural number with more than two divisors is called composite. And then some examples, 2, 3, 5, and 7 are prime. 4, 6, 8, and 9 are composite. Some trickier ones to determine, 51, 57, 87, and 91 are composite numbers, each with 4 divisors. What are the divisors of these numbers? And then I have a note here. Alexander Grothendieck is famous for a prime mistake. Alexander Grothendieck is a mathematician who focused a substantial amount of his life on algebraic numbers and trying to understand the structure of primes. At one point, someone asked him if he could give an example of a prime number for kids, and he came up with 57. The problem, of course, is 57 is a composite number. It is equal to 3 times 19. And so Alexander Grothendieck, who spent his life studying prime numbers, could not even come up with an example of a prime number. He was made fun of for that and eventually abandoned civilization to live in the backwoods of France. And so, fun character. The next one is the sieve of Eratosthenes. It is a strategy to find prime numbers. And so the idea with this sieve, which is kind of like an elementary program, is we circle a number starting with 2, and then we mark off all of the numbers which are divisible by 2. Then we move on to 3, and we mark off all of the numbers which are divisible by 3. And then we go on to the next prime number, which would be 5. So here's 5, and we mark off all of the numbers which are divisible by 5. We can see that process done here where all of the numbers divisible by 2 are marked out in pink. All of the numbers divisible by 3 are in blue. All of the numbers divisible by 5 are in red. And then we can continue with all of the ones divisible by 7, which we have in the dark blue. We have 49, 77, and 91. And then the next prime number is 11. The next value, which would be divisible by 11, just looking on the main diagonal, we have 11, 22, 33, 44, all of the way down. The next value would be 121, which means that every other number on here, which has not been marked off yet, is also a prime number. And so this is a strategy for finding all of the prime numbers up to a certain point. Since there's an infinite number of prime numbers, do this until you find as many primes as you like, but then don't waste a second more on it, because you could spend a lot of time doing this and there will always be more prime numbers. Now that we've got prime numbers, we can talk about the greatest common divisor. So the greatest common divisor, or greatest common factor, of two natural numbers a and b is the largest natural number that divides both a and b. We often symbolize this with GCD or GCF of AB. A similar definition works if dealing with more than two integers. And so if we had three or more values, we'd be looking for the largest natural number that divides all of the numbers. Every pair of natural numbers will have a greatest common divisor. If the greatest common divisor is 1, well, it's just 1. We can call that, or those two numbers, relatively prime in that situation. And so here's some examples. The greatest common divisor of 12 and 18 is 6, because 6 is the largest number which goes into both 12 and 18. 1, 2, 3, and 6 all go into both numbers. The largest one is 6. In the case of 45, 60, and 75, 15 goes into all three of them. And for 15 and 28, well, the greatest common divisor of 15 and 28 is 1, because 1 is the largest common divisor. It's the only thing that really goes into both 15 and 28. And so 15 and 28, we would say, are relatively prime. Here's a theorem. Let a and b be integers with the greatest common divisor of a and b equal to d. Then the greatest common divisor of a over d and b over d is equal to 1. Now, you might be a little concerned because you see fractions here, but these things aren't actually fractions. Because when we think about this, if d is a common divisor of both a and b, then that would mean that a divided by d would be some number, some other integer. D goes into a evenly. D goes into b evenly. And here's an example. Given 15 and 20, the GCD is 5. Well, what this theorem is saying is that if we divided out that 5, we would get the GCD of 3 and 4, which is 1. That's nice. So this is saying if we divide out by the greatest common divisor, we are always going to get 1. Here's another theorem. If a and b are natural numbers, then a positive integer d is the greatest common divisor of a and b if and only if d divides a and d divides b, so it has to be a common divisor. And if c is an integer which divides a and b, then c divides d. All right, let's see if we can understand what this one's saying. And so consider the GCD of 12 and 18 being 6. Any common divisor of 12 and 18, such as 2 or 3, must divide 6. And sure enough, any common divisor between 12 and 18, which would be 1, 2, 3, and 6, all of them go into 6 evenly. And that's what this theorem's saying. We're going to use that for the fundamental theorem of arithmetic. And so the fundamental theorem of arithmetic says every positive integer greater than 1 can be written uniquely as the product of primes, with the prime factors in the product written in non-descending order, or non-decreasing order. Writing out a number as the product of primes is called the prime factorization, and the process of finding the prime factorization is called factoring. And so this is saying no matter what number you choose, it can be rewritten as a bunch of prime numbers multiplied together, and some finite number of prime numbers too. And so here's an example. The prime factorization of 120 is given by 120 is equal to 2 cubed times 3 times 5. This prime factorization is unique. No matter how you factor the number 120, you will always get this same answer. Any numbers exactly made up of 3 2s, a 3, and a 5 must be 120. And so this is how the primes form the structure of the natural numbers. It's all just some multiple of prime numbers, and yeah, that's every single number. And so now comes the question, how do we actually find this prime factorization? How do we factor? And so to factor a number, we will typically use what's called a factor tree, as seen to the right. Given a number, so in this case 60, we just want to find two numbers that multiply to give you that 60. It does not matter what those two numbers are, as long as they're integers and neither one of them is 1. And so in this case, I said 6 times 10 is 60. Well, each of those can also be broken down. And so 6 is 2 times 3. 10 is 5 times 2. And so now we can look at all of those bottom elements. Every single one of them is prime. And once we've made it so that every number is prime, those are the collection of primes we need to put together. And so we have two 2's, so 2 squared. Then we have a 3 and a 5. So it's 2 squared times 3 times 5 is 60. What's interesting is it doesn't matter how you break it down, you will always get the same answer. And so if we did 15 times 4, well, 15 is 3 times 5. 4 is 2 times 2. You're still getting the exact same answer. And that's guaranteed by the fundamental theorem of arithmetic. And so no matter how you factor it, you're always getting the same answer in the end. Now that we have ways to divide and we're looking to factor quickly, we might need some tricks. And there are a lot of tricks out there. This list here, these are some of the more common tricks that you'll see, except for 7. 7 is kind of a weird one. But 2, 3, 4, 5, 6, 8, 9, and 10, those are tricks which we can do fairly quickly. And so how do you tell if a number is divisible by 2? Well, if the last digit is even. 4 is if the last 2 digits form a number that is divisible by 4. 8 is if the last 3 digits form a number that is divisible by 8. You could actually continue that on if you wanted to. For both 3 and 9, it's all about adding the digits together. And so if the sum of the digits is divisible by 3, then the number itself is divisible by 3. If the sum of the digits is divisible by 9, then the number itself is divisible by 9. If the last digit is 5 or 0, then the number is divisible by 5. If the last number is divisible by 0 or ends in 0, then the number is divisible by 10. And then there's 6. The number is divisible by both 2 and 3. I usually recommend skipping 7. 7's a little weird. Another thing we can do with these is the least common multiple. And least common multiples are often taught at the same time as the greatest common divisor, which means that they often get mixed up. And so the least common multiple of two natural numbers, a and b, is the smallest positive integer that is divisible by a and b. And we write this LCM of ab. As an example, the LCM, the least common multiple of 12 and 18, is 36. And this is because 12 and 18 both go into 36. 72 and 108 are also common multiples because 12 and 18 go into 72, and they also both go into 108. But 36 is the smallest of the common multiples. So that's why it's called the least common multiple. A trick to remember which one's which between the greatest common divisor and the least common multiple. The greatest common divisor is a divisor, meaning it's generally smaller than the numbers. A least common multiple is a multiple, meaning it is generally larger than the numbers. We can actually use factoring to find the least common multiple. And so given two numbers, we first find their prime factorization. And so we can factor the numbers. After we've done that, we're going to construct the least common multiple by creating a number which has all of the prime factors from both numbers. And so if one number has a 2 squared and the other one has a 2 cubed, the LCM would require all 3 factors of 2. Here is a sample problem. And so to find the least common multiple of 18 and 20, we start by factoring both numbers. 18 is 2 times 3 squared. 20 is 2 squared times 5. The LCM will need to have all of these factors. So the LCM of 18 and 20, well, it needs to have 2 2's because the second one has 2 2's. It's going to need 2 3's because the first one has 2 3's. And it's going to need a 5 because the bottom one has a 5. And so our least common multiple is 180 because that's 2 squared times 3 squared times 5. There's also a strategy for finding the greatest common divisor, which is kind of similar. And so given two numbers, we can find the prime factorization, and then we can construct the GCD by creating a number which combines the common factors which the two numbers have in common. And so in this case, if one number has a 2 squared and the other has a 2 cubed, the GCD would have the fewer of the two. Again, this is looking for a common divisor. And so we're looking for what both of them have in common. In this case, this example, 24 and 60. We start by factoring both. And so 2 cubed times 3 gives us 24. And 2 squared times 3 times 5 is 60. Now we look for what both of them have in common. They both have at least 2 2's, and so we would say it needs a 2 squared. They also both have a 3, and so we have a factor of 3. We don't need the extra factor of 2. We don't need the 5 because that's not something which is shared between both of them. As such, the greatest common denominator, or greatest common divisor, is 2 squared times 3, which is 12. It's the largest divisor, having all common prime factors. Give you some final thoughts on number theory. What was presented here is really just the introductory material, and it goes much, much deeper than this. Again, when we start talking about GCDs and LCMs, that is a pre-algebra topic. And so usually folks feel relatively comfortable with that. Maybe they might struggle with computations of it, but it shouldn't be too terrible. Much of the arithmetic you learned growing up is really just applied number theory. And so when you think of your division algorithm from grade school, or all of the multiplication facts you had to memorize, or how common denominators work and how fractions work and how you can add mixed numbers and any properties related to decimals, it's all just number theory. It's all just how can we play with numbers to try and understand their structures a little better. Number theory gives us a tool set for exploring the numbers we already know. While we focused on natural numbers, we can apply these same tools to other number sets. And so what do prime numbers look like when discussing algebraic numbers? Or what do they look like when we're talking about the Gaussian integers? How can we then apply these concepts to better understand rational and real numbers? And how can we apply these concepts to better understand the world around us? I mean, this is all just about number sets. And one of the things which is very, very important in this world is just trying to have some understanding of numbers and how we can divide things up, and do we have enough of something? And so this idea of number theory becomes very important. With that, I'll let you get to work exploring where you find number theory in the real world. Good luck, folks.